I will be the cameraman. That just means I need to make sure I work in the middle board.
Yeah.
So if you see me not working in the middle board, like yell at me or something. So I must begin with a word of prayer, as is customary. Dear Father, we thank you for this day. Thank you for all the students who came to this help session. Help us to make the most of the time, Lord. In your name I pray. Amen. I had an example for you guys that I thought might be helpful. So we talked about equivalence relations, right? So here's one. I thought might be interesting. We could talk about fractions, right? Like, when are two fractions equivalent? I mean,
like when one is the reduced form of the other.
Right. Well, one is, so is 1/2 equivalent to 3/6? Right? Or just say more generically, when is A over B equivalent to C over D? Right? So, in fact, we usually just write equality, right? Because this is one of the usual places where equality is used. But of course, this is, you could just say if and only if what? If and only if A times D is equal to B times C, right? For anyway, A, B, C, D here are understood to be integers, and fractions are, it's A over B such that B is non-zero, the set of all such things, right? So the equivalence class then, right, of 1/2 in this way of thinking would be what? It's, oh, yeah. Well, now I've begged questions I didn't mean to beg. Curses. I wanted to say this is like 1/2, 3/6, 4/8, et cetera, et cetera. I mean, and on, right? I mean, the equivalence class has all equivalent fractions. I mean,
Did you
depend.
skip like 2/4 on purpose?
No, just it's how I'm built. I mean, it's just my. Anyway, so my it's easy enough to verify that that's an equivalence relation, right? Any fraction is equivalent to itself, and you get transitivity, you get symmetry, right? I mean, it's pretty much because it's really equality, right? So I mean, and honestly, the thing that's bothering me is I'd really kind of rather say that this is this, but maybe. And say I would also say that that's equal to 2/4. Now, some people would like to say that 2/4 and 1/2 aren't the same thing. But if you're going to say that, then you're not working with real numbers anymore. I mean, there's some discussion that could be had there. I'm not. Let me stop talking about that. Get to a more interesting question. So suppose you want to define a function, right? So we can say f of, let's say, m over n, right, equals to, I don't know, m minus n, And you can ask the question, is that a function, right? And we'll say where f is a function from rational numbers to the reals, whatever. I mean, we could make it integers here, there, z. All right. Is this a function? So what do you guys think?
Well, you can put different things in and get the same thing out.
So like 1/2 is equal to 2/4, right?
Right.
But f of 1/2, according to our rule, would be 1 minus 2, which is minus 1, and f of 2/4 is equal to 2 minus 4, right? Which would be minus 2.
It's the same thing. We're two different things.
Right.
This is not a function.
Right. So this is not single valued, right? F not well defined because it's not single valued.
Does it matter too that like if you put in like I don't know 3/5 and 2/4, you would get the same number?
3/5 and 2/4 gives you the same number. I mean,
Right. Yeah. Like it both give you like -2.
well, having the same number is not a problem.
Right.
I mean,
Is that
you
like
know,
a parabola?
right? If you talk about like f2 is m over n, we could say that this is equal to 1 for all m and n. Now that would be a function. It's a constant function, right? And there's tons of things that are functions. I mean, the problem is not with the rational numbers. The problem is with, you know, using m and n in a rational number as if they're somehow not related, right? They are related through various ways. Now, if you used m minus, if you said the reduced, like you find the prime factorization, you cancel out, corresponding prime factors. After all that's done, you have the reduced, right, the fraction in lowest terms, and then you define a function based on that, and you use the, numerator minus the numerator minus the denominator of the reduced function, the reduced fraction. I think that's a function. It's, here's another one. If I had, f3 m over n, I could define it to be, say, n over m, That's going to be a function. So there's a nice homework problem which asks you a few different formulas about defined in terms of rational numbers. Is it a function or not? Rational number, it's such a well understood equivalence relation that we actually absorb the equivalence relation to our understanding of equals, right? Like there are people who will say 1/2 is not equal to 3/6, but I am not one of those people. Dr. Sprano sometimes is one of those people. And, I just disagree, but it's fine. I think we understand each other. It's just a different viewpoint. But so anyway, I just want to share that simple example about a well-defined function. You guys have questions? Now, just to set the rules of the game in here, I will answer questions about training exercises all day long, but I will not help with missions. So, them's the rules. I will clarify mission statements, but I will try my hardest not to actually start working mission problems. If you find me in a moment of weakness and I do it, it's not intentional. Section what?
We were just looking at the first few. I haven't looked at the training.
Section point 2,
Yeah.
number 8?
Yeah.
All right, let's look at it. All right, so here we go. We have A and B. And again, we're working from Nicholson, 4th edition. Anyway, so it's a basic set theory question. We have A and B are sets, right? And we're given what? Here's the thing we're trying to prove, right? What are we trying to prove? If A intersect X is equal to B intersect X, right? And what else? A union X is equal to B union X for some set X. prove that A equals B. So that's the problem. He's given us a hint that A is equal to A intersect A union X.
Which kind of,
It's like, I guess, okay, sure, why not? A is equal to A intersect A union X. Is that right? Maybe with that hint, this might just be algebraic, but really, it's really not kind of my intent with this kind of problem. But, stink. All right. Let me try this out here. So we can start with A equals to A intersect. I haven't tried this yet, guys, so this may or may not work, okay? Then we're given what?
that is equal to B.
Right, so A intersect B union X. Let's see here.
Then B union X has to include all of A.
Huh. So your point is that this implies that A is a subset of B union X?
Oh, yeah. I guess we already knew that.
Well, yeah, I think that's immediate from this, isn't it?
Yeah.
Substituted A intersect A union X for A in one of the equalities given above, and like
Well, you're saying instead of using the hint by its lonesome, try to use the hint up here. Something like that? All right. Yeah, this doesn't seem to be going anywhere. I mean, let me just erase this. It doesn't seem to be helpful. All right. So if not, try again. So A intersect X, like you said, we'll replace, that's equal to A intersect A union X, right? Intersect X.
so that we can turn that
And that itself is equal to B intersect X, right? Or that wasn't your, I mean, anyway.
that was
Okay.
But we know A union X is B union X.
A union
In the
X
middle.
in the middle is, that is true. I like that because this altogether uses the one given. And now you're telling me a meaningful way to introduce this data.
Do you need another set of parentheses to say, to like separate the A intersect A union X from the union with X?
Yeah, probably. Let's see here. I'm sorry.
The second parenthesis.
Like that, yeah. Okay, so this, you're just telling me I should really write that A intersect B union X, maybe. Maybe that'll be helpful, right? Huh.
Can you distribute the intersection, A intersection B,
Oh, yeah.
union A intersection X?
Distribute the where?
So it'd be A intersect B, union A intersect X, all intersected X.
So you're claiming that we know this is A intersect B unioned with A intersect X. Is that a property of set theory? Intersections distribute across unions like that? Okay. Okay. So I
So
can,
now if we could show that A
Can I do that
intersect
again?
B was equal. Oh, yeah, we can do it again.
I mean, is this then, I mean, I don't know if that helped or not, but A intersect B intersect X, right? Union A intersect X intersect X. Is that? Sorry, bad notation.
If we, yeah. I guess we started with A intersect X is equal to A intersect, or B intersect X. So we can we resubstitute that down here? Like, are we allowed to use that?
I don't know, guys.
I don't know if that's going to help. Let's see. Okay.
Yeah, I think we're meandering.
Because,
Yeah.
you know, at the second step, we ran into the same problem that we're trying to prove. Because if we could show that, you know, the first part is equal to B, but that's the whole point.
Yeah, let me try a different. So, like you know, if you see how to use the hint, then great. I'm sure the minute after I post this video, someone in the YouTube will be like, "Hey, it's blah blah blah." I'm like, "Oh yeah, no, great." Let me take this opportunity to try to chase points. See if it works. Okay. So I'm trying to show that I'm going to assume that A intersect X is equal to B intersect X, and the unions are also equal, right? Now, if X is the empty set, then what?
That implies that A is equal to B.
Yeah, that's
The intersection's empty set, and then
A union empty set is A, B union empty set is B, A equals B, done, right? So if X is empty, we're done. If X is not empty, then there's some element in it, right? I'm not sure that it actually matters or not, but we're trying to prove A is equal to B, right? So let A be an element of A, right? And A is equal to, I'll use this hint now, tell you what. That's A intersect what? A union X, right? Which is equal to A intersect B union X. So what's that mean?
A is also in B union X.
So thus, right, A is also an element of B union X.
Are we allowed to like assume that much?
Oh, that's the definition of intersection.
Okay.
I mean, to say that an element is in an intersection means that it's in both. So by definition of intersection, A is in B union X. We also know A is in A, but who cares? Yeah. So that means what? A is an element of B, or A is an element of X. So if A is an element of B, then we've shown what? We've shown that an element in A is also in B. So that shows that A is a subset of B. Now, on the other hand, if A is an element of X, right, then what? There's two things that could happen. Yeah.
Oh, then A is in A intersect X, which means that it has to be in B intersect X? Wait, which means
Okay.
that it has to be in B.
Oh, very good. This implies that A is an element of A intersect X, which is equal to B intersect X. Work. Hence, A is an element of B. Therefore, A is a subset of B. Yeah. So I a lot of times find that chasing points
Yeah, that's
is a more, it can often be a more straightforward, these kinds of problems anyway. Granted, once you sort of have a better vision about what's going on, you can do them symbolically using the distributive property like you guys were trying to do. It's just we kind of got lost in the weeds there. There is doubtless some pointless argument which can be given here. I just don't see it right off. Pointless in the sense that I don't. Now this is half the argument, right?
Yeah, that was
But by symmetry, the same argument will show that B is a subset of A.
Can we just say by symmetry?
For a problem like this, yeah. It depends on the problem, though. It's it's a question of style, whether or not you should use it in different places. I mean, here it's fairly clear that the role played by A and B is symmetrical, so it's an appropriate use. All right, we did a problem. What should we do next?
We can keep going.
Keep going, all right.
Okay. Section point 3, number 11.
Let's see here. So some question about a bijection. Let's see here. So we've got M denotes the set of all mappings, all functions, if you will, of the form what? Alpha. That goes from the set containing 1, 2, right? To where? To B. What's B? I guess it's a set. He didn't tell us, did he? Let's assume B is a set. D says define phi that goes from M to the Cartesian product of B and B by phi of alpha is equal to, what is it? Alpha of 1, alpha of 2. Right? He says, show that phi is a bijection and find the action of phi inverse. Not a lot to work with here, right? Now we got, how can we show something's a bijection? What's that mean, to show that phi is a bijection? Right. Now, we could do that, right? And find phi inverse. But I guess my point here would be, we have a theorem that is just stated, which says that if the inverse exists, the function is a bijection, yeah. So if we could find the formula for the inverse and prove that it's actually an inverse, I think we'd be done. Let's see, so phi inverse should do what? Phi inverse should be, take what?
Alpha of 1, alpha of 2.
Right, let me say x comma y, right? Here x and y are where? B, yeah.
And
Yeah.
or 1, 2. No.
It should be, it's got to be something, it's got to be some element of m, right?
Right.
This is supposed to equal alpha, right? Somehow, I mean, we have to come up with the alpha in terms of x and y, right? But if I mean, it's a map in M, right? So to define this, we need to say what phi inverse xy, when we feed it 1, what's it do? And phi inverse of xy, what happens when we feed it 2? I mean, if this thing, whatever we're trying it to, we don't know what this is yet, you know, but if I can tell you what it does to 1, if I can tell you what it does to 2, then at least I've defined this inverse. Because it's supposed to be a map on the set one that tells me where to send 1 and 2, you know. Yeah. I think there's really only one thing to do. The output has to be what? Something from B, right? I mean, this alpha does what? I mean, alpha alpha of 1 and alpha of 2 are supposed to be elements of B, right?
Oh, yeah.
So I need to send 1 to some element of B. I need to send 2 to some element of B.
So just put 1 as x and 1 as y.
Very good.
Okay, so I'm a little confused of what alpha is defined as. It's just the only thing you can put into alpha is the set 1, 2, and you'll get something in B.
I might, let me,
So phi inverse is a mapping between B cross B to M, which is all maps L.
right.
I'm a little confused about the alpha.
I like to use the following notation, by the way. M is functions from 1, 2 to B. Sometimes it's helpful to have a notation for the set of functions from one set to another. That's my notation.
Oh, okay, so that's just the set 1, 2, and then it's going to another set, which we don't.
Yeah, B is just,
Okay.
it's out there.
That makes sense.
See, what's bothering me is the inverse should be unique, you know? If it exists, the inverse is supposed to be unique. And I feel like I could send 1 to y and 2 to x just the same. Something I'm missing here. I hope it's not one of these problems where there was further, you know, stuff told to us about B in previous problems we're not appreciating. I don't think so, though. Hmm.
So, wouldn't,
Hmm.
so if phi is mapping, if phi inverse is mapping, well, the way I think about it, phi inverse is mapping backwards.
Yeah.
So x would be pretty much alpha 1, and y would be alpha 2. So you plug
Yeah, yeah, that's right. That's what we're proposing.
So then,
Right. I mean, I'm using two different notations for alpha. One is this kind of obnoxious.
no, what I'm saying is if you, so then if you plug in x for alpha 1, the only thing you can get when you evaluate that at 1 is x. If that makes any sense. That's why it's unique, because it can't be y, because that was alpha 1.
Huh. Oh, well, let's just try it out. I mean, you're probably right. I hope you're right. I mean, there's something I don't understand about this problem, so I'm not sure where my gap is, you know?
Just kind of throwing something around a corner that you can't see on the
So if this is actually the inverse, we can try it out, right? I mean, we can try to calculate the inverse, right, of phi inverse of phi of what? Phi takes in,
It takes in alpha.
I've lost track of what phi is. Phi
Oh.
of alpha, right?
Yes.
Phi of alpha. So that's phi inverse of what?
Alpha 1, alpha 2. Which alpha of 1 should map to something in B, and then alpha of 2 should map to something else in B.
Let's see here. So let's call this thing. Let's call this using alpha here and there is unfortunate. Let's call this gamma just for a second. All right. So this is gamma. I'm sorry. Not that one. Sorry. So I don't have words. The inverse of phi of alpha. This is supposed to be a map. What happens when we feed it 1? We get alpha 1, right? And likewise, we get 2 by our definition here. That's why I couldn't switch the roles of x and y. If I had done that, it wouldn't have actually been an inverse. I would have gotten 1 is alpha of 2 and 2 is alpha of 1, which would mean, see these being equal for 1 and 2 implies what? That's all values of the map. So this says phi inverse of phi of alpha is equal to alpha. Which shows you that at least one half of the inverse condition is met, right? We should check the other composition as well, right? What was the other? We also need what? Phi. Right. Of what?
Alpha 1, alpha 2.
Yeah, let's say xy.
Okay.
Right, so we're supposed to do, what was our rule?
Oh my gosh, okay.
So phi of alpha does, so phi does what? It does phi inverse of x comma y of what? Of 1. Phi inverse of x comma y of 2. This is the definition of phi. It takes this, which this is our quote unquote alpha of the original definition. And then what's our definition? Phi inverse of x comma y of this is x, and this is y. X and y being arbitrary elements in the Cartesian product of b and b, we've shown that, in fact, your formula for inverse is right. And my doubt about the possibility of flippity-floppiting the x and y doesn't matter. Yeah. Well, this problem is way more difficult than I thought it was when I assigned it. I mean, it's a good problem. I think it's important to think.
It was kind of easy to see it, though, from the beginning. But then when you try to, like, show, like,
This problem is quite abstract. I mean, there's really not a lot to hang on to here except for 1 and 2. You know? Let me try to pick a different problem from this section, which is, you know, maybe good. Let's see here. We could try to do like 3a might not be bad to try out. So 3a says that if beta alpha is on 2, show that beta is on 2. This invariably happens in here. I pick a lemon to work on, you know. We end up we somehow gravitate towards the least interesting problems in the, yeah. Let's see here. 3a. So it's simply this. We have A, we got B, we got C, we got some maps. The maps are alpha and beta. And the question is to show if beta alpha is on 2, all right, then beta is on 2. Let's see here. Let's look at the proof. So our beta is what? Beta is a map from B to C, right? And how about beta alpha? Beta alpha is a map from where? A to C, right? We assume beta alpha onto, right? Okay, so to prove beta is onto, what should we do? We should pick an arbitrary element of C, right? Let C be an element of C. What do we need to do? We need to provide some element in B such that beta of whatever that element is gives me back C, right? Since beta alpha onto, right, there exists what? A and A, right? Such that what?
Such that beta alpha of A equals C.
Right. Hence what? Beta of alpha of A is equal to C.
So beta of, okay, so alpha of A gives you something of B, right?
Right, therefore, alpha of A, which is an element of what?
B.
B, has beta of alpha of A equals to C, hence beta is onto. In fact, alpha of A was that arbitrary element we were looking for. And the proofs of most of these are pretty similar to this. I mean, you just have to use the definition of onto or one-to-one and you can prove number 3.
I was looking.
This would be good like math 200 problems, right?
Yeah.
Yeah.
I was looking at our mission and like, the first example you did when we got in here, like, showing that it wouldn't be a function, like going from the rational to the integers, the n minus n. So like, on number 7, if we were to show that it is a function, would we just have to show that it's onto and one-to-one?
Well, not all functions have to be onto or one-to-one. So your question was in number 7 of section 4, which is problem 1 on mission 1. You know, what is,
7, C, and D.
how do you, yeah, part C and D. How do you show, the question is in each case determine whether alpha from positive rational numbers to the rational numbers is well defined, right? Support your answer.
So I know how to show if it's not well defined.
Right.
But I'm a little confused on how to show if it is.
To show it's well defined, you should show that if you have two equivalent fractions, that it produces the same output,
Okay.
right?
Yeah.
So basically,
And you would just have to like assume.
I mean, you can use different notation, but you can say like m over n equals m prime over n prime, and then show f of m over n equals to f of m prime over n prime, given, of course, this condition. That would show it's single valued. Yeah. Other questions? Number 9, problem 2 in mission 1, also from section 4, is it's an interesting problem, I think. Let's see here. I can start talking about that one at least. I probably won't do it, but let's see here. Ooh. Huh. Oh man, I cut out so many interesting problems. I got to go back and do one of these. How about this one? We're supposed to show that blah is an equivalence on A and find a well-defined bijection. All right, this actually might be helpful for 9. This example, perhaps. Let's try it out. Part number 3. This is section 0.4. Number 3, part. I kind of like part B. That looks fun to me. So the equivalent, we're looking at A is, what is it? It's the Cartesian product of the reals and the reals, right? And the equivalence that we're proposing is that x and y are equivalent to x1 and y1. What's the criteria for the equivalence? If and only if what? He says x squared x squared plus y squared equals to x1 squared plus y1 squared. Can you guys put that into words for me? So we're supposed to show that that's an equivalence on A and find a well-defined bijection to B from the quotient set of A. So we're supposed to find bijection sigma from A quotient set to B. That's the whole problem, yeah. I really like this problem. It's very geometric, actually. What is that? What is equivalence, actually? What does it say? When 2 points are equivalent of what? Right, but what does that mean? I mean, geometrically, what is x squared plus y squared?
Circle? No.
Right, if I set it equal to a constant, it's a circle, true. I mean, yeah, so if these are both equal to some other constant, then that means they're both on the same circle. There you go. This means that the 2 points are equivalent if they're on the same circle.
Okay.
Another way of saying it is they have the same distance squared from the origin. Right? They could both be points at the origin. The origin is equivalent to itself. But all of the other equivalence classes are actually concentric circles around the origin. So this is the picture. You have the lonely origin, and then you've got circles. Your equivalence classes are circles. Like, so here, this would be the equivalence class of 1 would be the unit circle. The equivalence class of a half. Well, I mean, let me do a fourth. Oh, sorry. I can't do that. I'm an idiot. I should say 1, 0, right? If I had a bigger one out here, bad, but I'll do it down here to keep my picture cleaner. Suppose this has radius square root of 2, right? So this would be like 0, yeah, thank you. That, yeah.
Okay, so the equivalence class, like, you couldn't do 1 because it has to be one of the points in the class.
Yeah, the equivalence class has to be generated by something in A. Here, A is Cartesian products of the reals, right? So it has to be a point in the plane that generates the class. The class itself, though, geometrically, it's either a circle or the origin, yeah? Now, what are we asked to, I mean, I guess you could say, okay, prove that that's an equivalence relation. So is any point equivalent to itself? Yeah, because, I mean, x squared plus y squared is equal to x squared plus y squared. Yay. Is it symmetric? Well, yes, x squared plus y squared is equal to x1 plus y1 squared. And yes, also, x1 squared plus y1 squared is equal to x squared plus y squared. It's defined in terms of equality. So like the transitivity, the symmetry, and the reflexivity pretty much come because of, this is like, there's tons of examples like this. Checking symmetric, transitive, and reflexive is really boring. It just basically comes down to it's equals. Okay. But, okay, so it is an equivalence relation. I haven't written that all out, but it is. The equivalence classes, I've tried to draw you some pictures of what those are, right? To be more specific, here's it in gory detail. If I have A comma B, the equivalence class, what is it? That's x comma y such that what? X squared plus y squared is equal to a squared plus b squared, right? That's the equivalence class. Now B is what? B is, you could view it in our picture geometrically as the ray of, it's the x-axis, the positive x-axis, right? I mean, you could look at it that way. Or if you want, you could picture it over here. It's 0 to infinity, right? This is B. So we're supposed to give some bijection. What's our bijection? That takes in the equivalence class, A comma B, right? and it spits out a non-negative real number. What should I do?
Could it be a squared plus b squared?
But then, could it be a squared plus b squared? I think, yeah. Very good. I was thinking something more like dumb. No, it would have been the same thing. I was just making it more complicated. I was thinking of using, here's what I was thinking. I was thinking I'll take this line, I'll draw it back here, and then I'll use the x-coordinate of where the circle intersects this line as my map. But with the place where the circle intersects that is going to be, x is going to be the square root of a squared plus b squared. This point will be square root of a squared plus b squared, comma 0. My map is your map with a square root. But good, I think yours is better. And then the question is this a bijection? First of all, is it well defined? Right? If I pick something else in here, if this is equal to, x comma y, if I have xy is equivalent to AB, then, this is equal to x squared plus y squared, right? But because they're equivalent, it's also equal to a squared plus z squared, so hooray. It's a well-defined map, right? It doesn't matter the representative we use, we get the same output. And then what else? Phew, almost done. So I'm trying not to go over on you guys. Although I will if you have, anyway, I'll get in trouble if I stay too long. It's well defined.
Right.
It's definitely into, like I talk about into. Into means that it actually, the codomain is well stated.
Okay.
But sometimes people will say that's well defined too. Like what well defined means is not, there is some debate about that. But B is non-negative. Certainly the sum of squares of real numbers is non-negative. Okay, so it's definitely into. And then the natural next question is, what's the inverse? Like if you can tell me what sigma inverse of R is, where R is an element of this guy, right? A non-negative real number. So you got to give me the equivalence class, right?
Could be R0.
R0. Let's see, that has,
I guess you could do 0R too.
I don't, but that maps to, I don't think that's quite right because, that's a good idea, but I think if we try sigma, right, of sigma inverse of R, what happens with your map as it stands? What do we get? We get R squared, right? The fix is very simple. Square root. With square root, then when you do this down here, you get square root of R squared, which is R again. And it's easy to check that the other composition, sigma inverse composed with sigma, also gives me back what I started with. So in fact, sigma is a bijection. So sigma also is sometimes, so this is what I sometimes would call like a cross-section. Cross-section is something like, it's like a way of taking a bunch of equivalence classes and, like chopping through them in such a way that you just hit one of them in each point where you cut through them. And so then you can use the points of intersection as labels for the equivalence classes without ambiguity. There's great ambiguity in this A and B, right? But this right here is an unambiguous. I mean, the circle has radius a squared plus b, radius squared a squared plus b squared, right? That's unambiguous. Even though the point on the point which generates the circle is ambiguous. I mean, there's lots of different points which generate the same circle. So finding this bijection has something to do with finding a unique representative for each equivalence class. I think having this discussion should help make problem 9 make more sense. It's kind of the same wheelhouse. But anyway, probably next time we'll be knee-deep in modular arithmetic. So, but you guys can ask me about whatever.
We will be posting videos.
That is the plan. Supposing my camera works and I remember to actually hit record, stuff like that. Hopefully I turned on my mic. That would be sad, wouldn't it? Oh, yeah, audio working. Hooray.